Thank you for joining this session of Shadow the Scientist. My name is Jamaica Marshall, and I'm pleased to serve as the Shadow the Scientist Programs Manager. And the Shadow the Scientist initiative is brought to you by a fabulous team at the University of California, Santa Cruz. Now, this is a special session for the students in the California-Hawai Astronomy Mentorship Program. It's so great to see all of you. I did intend to be right there with you at the Hilo Base Facility this evening, but I was just not feeling at my best, so I apologize for not being there in person with you, but so glad to have you. Now, let me just start my video here. You probably already know this, but for those who are not aware, the International Gemini Observatory consists of twin 8.1 meter optical infrared telescopes located on two of the best observing sites on the planet. Now, the Gemini North telescope is located on Hawaii's Maunakea, which I believe you all visited either today or earlier in the week. And so you know that Gemini North is part of an international community of observatories near the summit region. Now, by incorporating technologies such as laser guide star adaptive optics and multi-object spectroscopy, astronomers in the Gemini partnership explore the universe in unprecedented depth and detail. Now, tonight's observations, of course, will be taking place in the Hilo Base Facility, where you are just down the hall in the control room. And we have the privilege of shadowing members of the Gemini Observatory Science Team, Jen Miller and Mateus Rodriguez. Now, before we hear from Jen and Mateus, let's start with tonight's science host, Brian Lameau, to get us started. Aloha, Brian. Welcome.
Aloha, Jamaica. How's it going?
All is going well. All is going well. I'm super excited to be having this session for these brilliant students. Welcome, welcome to everyone.
So yeah, welcome everybody to Gemini, at least to our conference room, our very warm conference room for the evening. We have a lot of chairs here, as you can see. Exciting. So yeah, this is where we do the observing. So there, you guys are going to Mauna Kea on Thursday, right?
Yes.
Yeah. So you're visiting Canada, France, Hawaii, and Keck,
Yes.
right? Okay.
Oh, okay.
Yeah.
You
So
haven't been up yet. I apologize.
Well, HP tomorrow and Summit on Thursday.
okay. So you go to Halipaku for
Tree planting.
for tree planting and weed tending, right? Yeah. Okay. Yeah. So about half of the Mauna Kea observatories observe remotely. So CFH is one of them. Half of them have people up on the summit, and Keck is one of them. And so we're one of the telescopes that has absolutely nobody up. So if something goes wrong, something physically goes wrong, we have to drive up and do something about it. So if the fire alarm goes off, we have, as you can imagine,
Heck, don't you?
yes, but then we we call on the road. That's right, Dave. So yes, it's a friendly atmosphere up there, and everybody helps everybody. But yeah, so we have thousands of sensors. We have about probably 30 cameras or something up there that keep an eye on different components of our summit facility, whether that's, so we have 5 levels to the summit facility, whether that's level 5 where the telescope is and the instruments are, all the way down to the bottom level where actually one of our instruments are, and a bunch of other flammable things are. And so we monitor all of that from here, and we take the observations from here. So there's a fiber optic connection up to the summit that allows us to take observations from here with almost no lag.
Who tops off your LN and helium and all that?
So we have day crews that go, yeah, so right now they just switched to a 4-day-a-week schedule. They were doing a 5-day-a-week, and now they're doing 4-day-a-week with a full crew.
Through the weekend on.
Yeah, no problem. Yeah, that's not a big deal. So as I mentioned to some of you before, we're a cube-based observatory primarily. We have a classical component to our observatory. So classical, for those of you who don't know, means that you're actually at the telescope or you're in some way involved in the observing process. And Q is you're also kind of involved in the observing process, but you're involved in the sense that you prepare observations beforehand and then you throw them into this giant matrix of observations that a staff member here takes and makes sense of, and then makes a plan for the night.
That's Q driven, so you don't know when your observation's coming up, is that right? I was wondering whether an observer could zoom in.
Yes, so we have eavesdropping. We offer eavesdropping. Yeah, so actually every
Know
night.
that they have a probability of getting on tomorrow night, or is that your
No.
choice?
No, so we have two roles here at the observatory at nighttime. Well, there's a support structure, but in that room, there's two people that are in charge of the telescope for the night. So Jen, who's in the foreground here, she's our observer for the night. So her role is she has like the scientific roadmap for the evening. She has our Q coordinator, which is a role that some of us play at the observatory. They make 13 different, somewhere between 10 and 15 different variants per night. So we can show a little bit later, but how many people have observed on Maunakea telescopes? Dave, keep your hand up.
Not everyone.
Uh,
Is it the nice to Jen thing, or does the person in control make the ultimate decision of what goes, or is it?
No,
strictly
Jen's in
by
charge. Jen's completely in charge. So she has the map, but she doesn't have to follow the map if she doesn't want to.
That's what I was asking.
Yeah, if she feels like that there's generally the map is followed, but of course on Mauna Kea conditions are like things could be going great and then all of a sudden fog comes up and you know you have to close the telescope or clouds come or Kilauea goes off. There's all sorts of things that can happen, and conversely you know, predictions, even in the afternoon. I mean, we have predictions from the Mauna Kea Weather Center that's basically morning and afternoon. Those are updated, a supercomputer model, multiple models actually. And yet we get to the telescope even just a few hours after those predictions, and they're nowhere near the actual conditions are nowhere near what's expected. And that could be for better or for worse. Usually it's for better, actually. So I guess the models are conservative. But so Jen has these different variants, and each scientific program specifies the worst possible conditions that they can observe in. So we are contractually bound with the scientists not to observe in conditions that are worse than what they specify, because we say, no, we know better, and we don't trouble,
Right, yeah.
if we don't get the signal to noise, then we have to give them the time back and do it again. So, and sometimes, you know, there's an art to it, because for those of you who observed, I mean, there's a relationship between signal to noise and, for instance, cloud cover, image quality, so the point spread function, the surface brightness. So depending on which band you're observing in, these are all factors that you have to take into account when you're determining what is the expected yield from your observations, how well the telescope is performing, how well the instruments are performing. So yeah, this is complicated calculus, and we break it up into like quartiles or quintiles of different conditions. But of course, binary or trinary or quaternary thinking is not great in astrophysics. So there is an art in between these spaces. And so Jen is the scientific driver for tonight. She has the map. She has all the variants. And if, like, for instance, so we're taking a imaging program of a rapid target of opportunity right now. We will throw the data become available instantly, effectively. So it's not PFS. So within 10 seconds, the data are available to grab from our archive. And we have some automated reduction routines, especially for imaging, that work very fast. And so they can reduce their data. They can get and reduce their data within a matter of 20 minutes or so. And it's actually quite common for, especially for these types of objects, for them to do imaging, reduce the data, find the counterpart, and then trigger again. For spectra.
So they're on now?
They're on right now. Yeah. So the actual,
That's insanely fast.
yeah.
Get your data reduced and able to look at it. And under half an hour.
I'm trying to do that with SMA.
10 years.
That's like outrageous.
First, you gotta get CASA to work.
Yeah, data reduction. So Jamika, were you sharing the screen just now? Was that you?
Oh yeah, I was just showing,
Yeah, cool.
live view of the summit. Keck was just, turning around, everyone's opening and doing fun things. So I just had it on in the background while you were chatting.
Okay, cool. Yeah. So it is a beautiful night. Let me bring up our Oh, sorry. So just to finish the thought, so the other role tonight is operator, and that's Matty. So he's well, I just started sharing screen, but let me stop for a second. So Matty's in the background there, and Matty is our superstar in charge of the telescope. So he actually moves the telescope. So when Jen says move, he says okay, or he says nope, I don't want to do that, or nope, I got to close up, there's fog coming, or I don't know, some combination there. So he's also in charge of like all of the health of the subsystems, the telescope, the dome structure. He opens up our shutter at nighttime. So any like mechanical issues, he is our first line of defense. And both Jen and Matty are trained in different roles than I am. So they're science operations specialists. So they trust them to actually drive the telescope. They don't trust me to drive the telescope.
They have authority over you in that sense.
It
They can close if they want.
it's kind of shared leadership structure in
Okay.
time. So there's a nice dynamic in the sense that the scientist or the observer's job is really to push the operator to try to get as much data as possible. And the operator's job is to push back and say, no, our systems can't handle it. And so that's a nice dynamic. And the operator can close, and it's non-negotiable.
That's what I meant.
Yeah. But the observer has one superpower, which is that they can call the night whenever they want. So they can say, "Oh, I'm done. The night's over." But they're only supposed to do that if it seems like there's no chance of getting good data for the rest of the night.
So yeah, if conditions were like bad enough, but not bad enough to close, you couldn't get usable data for any of the programs, basically.
We've had cases where observers have flown in with a new instrument and they're going to get data no matter what.
Yep.
And can't let that happen if it's
Right. Yeah.
icy and ready to snow.
We're in it for decades. We're not in it for one night. Yeah.
Good.
Yeah. So I mean, and yeah, so we have very strict thresholds for all sorts of things for humidity, and that humidity threshold changes if particulates are in the air. So if Kilauea is going off, combination of SO2 and humidity is a very bad one for telescope optics. Dust, of course, is a problem. So wind speeds are something that we take into account. Temperatures to a certain extent, fog, rain, of course. But yeah, we have a lot of weather monitors, and we also share all of our weather data and our particulate data across the Maunakea observatories. So this is where we're not an island universe here.
Big happy family.
I'm gonna close it so I don't get feedback.
Does every telescope have their own enclosed monitoring system, or is there one chief person? I was asking the operators.
Yeah, it's not everybody has their.
CFH would control everything.
Okay, yeah, I mean, we piggyback off of CFH quite a bit, but like I think so that we have like particulate counters, for example, everybody measures like a different range. And so it's actually helpful to have all the different particulate counters to be able to like kind of, are you worried about big particulates? Are you worried about small particulates? So we have all of that linked to like on our nighttime like sheet that has all of the tools that we use. We have Subarus, we have Kex, all shared.
Yeah.
Exactly.
Well, that's nice. That means nobody has to pay for the whole suite, right? You just be like, I'm only worried about this size. So I'll buy this.
Right.
Or this is what we need, so I'll buy that.
Okay, so this is actually a public page. So if you were like, let's say you were the team that triggered the rapid target of opportunity tonight, you would actually go on this page, and so we have if all sorts of information on here, but this is all of our instruments that are available for tonight, and actually Genius is not available, so I'll yeah, talk with our Q coordinator about that. And then there is a transit tonight, so we actually do planetary transits very often. We have two. I'll get into the instrumentation in a little bit, but we have two very high resolution spectrographs. The Sigrans 2 is a H and K, so 1.4 microns to 2.6 micron spectrograph. That's, do you guys know R numbers?
Yeah.
I know you don't do.
Thousands or what?
So this one's 45,000. Yeah. Yeah.
That's
So-
the resolution of the
Yeah.
spectrograph.
Right.
Bigger
Exactly.
number, better.
Yeah.
Delta lambda.
It's yeah, it's lambda over delta lambda. So if you're observing in the near infrared, let's say the average wavelength is like 2 microns or something like that. So then R 45,000, you can, so it's yeah, it's like 1 meter per second resolution, something like that. So if an object in space is going more than 1 meter per second, which 1 meter per second is like then it can measure that. And Maunakea is an optical spectrograph, which is R of 80,000. So it's these are both planet hunters. So they're some of the best instruments of their kind on the planet, and they are
Is that planetary? I mean, who uses that sort of?
mostly planetary, yeah, planetary science. So planetary atmospheres, this is usually what we do. So we observe, like, so you have a host star like this, observers over there, Gemini's over there. And then you have the planet coming around, you have the ingress portion, then you have the occultation, and then the egress, like that. And it's basically a difference of the host star. So you measure the change in the absorption strength of the different features. And so you can get a handle on the planetary atmosphere, which is like super kick-ass. I mean, that's alien hunting, so that's not a bad deal. And yeah, it's so we have programs that survey the whole like local neighborhood for other stars, and they do this over many semesters. We have lots of transit programs, but it's like a lot of high cadence. So like observe every one night for like 20 minutes, or so this is like perfect for a Q-based observatory. But we can interrupt it by other observations that take precedence on a given night.
And your queue is the most heavily oversubscribed thing on the summit, as far as I can tell. Is
It
that-
fluctuates a lot. I would guess PFSQ is pretty oversubscribed at this point. So for those who don't know, prime focus spectrograph is great. Dave, you're not allowed to raise your hand, but prime focus spectrograph, you guys know this? Okay, so this is a new instrument on Subaru that has like 2,400 fibers. So you can take a spectrum of about 1,600 science targets all at once. The other 800 are used for calibrators. And so this is like, I mean, it's by far the most powerful spectrograph on the planet. And so people are very, very excited to use it. So
We got
several people.
in the room that got more PFS spectra than anyone else.
Yeah, I
Actually,
think that's
just,
actually probably true. Yeah.
The rest of my data was reduced like an hour ago.
Run 23 or whatever.
Yeah,
it is.
Run 23
Okay,
came out.
yeah. Cool. Yeah. So yeah, so I mean, Subaru Keck, they're kind of like lumbering beasts. I mean, they get set up, you know, like this spectrograph is insanely powerful, but 2,400 fibers, it takes a lot to like reconfigure everything. And so they go to a place and point and they integrate. Gemini is like super squirrely. It's just like, what's that? Oh, okay, 20 minutes over here. Okay. Oh, something just blew up over there. Okay, we're gonna go over there. So the telescope's fast, the instrument switches are fast. We have all our instruments on at a given night. So I'll show you guys later how the optics work, but we have basically everything in this cage that we can just move a tertiary around. Yep, exactly. So actually the instrument switch time is a lot quicker than the slew time. And the slew time is fast.
That's crazy.
They all mounted on platform or
The
what?
instrument support structure on the back of the telescope. Yeah. Yeah. So it's not even Naismith. Yep. It's gas gauge. Yep. We have one. So Maunakea is a fiber, and the fiber actually. So this is the instrument that's at the bottom floor of Gemini.
How long is the fiber?
It's like hundreds of meters.
Yeah.
Yeah. Yeah, so it actually, there's just this one fiber going off the back of the telescope. And it goes all the way down to the basement where Maunakea lives.
Is Maunakaea's just enormous? Or
Sorry,
is it just really big?
it's
It
pretty
can't
big,
fit
yeah,
up
but
there,
it
or-
can't move. That's the thing. Like you don't want it anywhere near no vibrations, because like we have an instrument called GNIRS, which I'm the instrument scientist for, and it has cold heads to keep it cold that oscillate and they create some shaking. So you don't want to be doing that with like really high precision instruments.
As close to the rock as possible.
Yeah, exactly. So yeah, so this is the view. These are all our cameras except for this NNIO, which is CFHT. This is a difference imaging for cloud cover, but we have the satellites up. We have the wind direction where we're pointed right now. This is a bird's eye view of the telescope. And then Hilo, look, it's a little clear. Wow. South cloud. So this is, you can see Kilauea going off when it's going off in the south cloud camera.
Oh, yeah, we could use that as a monitor.
Yeah, exactly. Exactly. So if it goes
So
off,
the
then we can.
immersion layer's low and you've trapped all the.
Yeah, it's pretty low tonight, actually. Yeah. It's nice. You can even say Waimea, which is actually pretty rare. Yeah.
Another thing for, I don't know if you guys have noticed, but like, it's been crazy cloudy in Hilo the whole time we've been here. Even if it looks cloudy from Hilo. Hopefully it should be perfectly
Just crystal clear, yeah.
So clouds like sink below. the
Right below HP, it's
Yeah.
like
Yeah.
at the
10,000 feet, yep.
level, so. We'll see that when we drive up tomorrow.
Very
Break
pretty.
through and all of a sudden it'll be a miracle.
Yeah. So yeah, it's not common. You get to see it in the morning, Maunakea in the morning, usually the summit in the morning from Hilo. And in the evening, it'll usually drake like for a little bit. But yeah, during the day, it's usually pretty cloud and shrouded. And then at nighttime as well. It's pretty rare that you can see all the way there. Yeah, so like when Keck is
Don't have any spotters.
no, nobody has spotters. No. Yeah, Lick. So I was at UC Santa Cruz and UC Davis. That's where I did like most of my studies, and we use Lick Observatory on Mount Hamilton, which I guess from Riverside. Has anybody applied there or Lick Observatory? No. Have you guys know that there's like a summer school over there? Yeah, you know that. Yeah, it's I didn't actually go to summer school. I just like decided to PI my own programs because you can as a grad student or as an undergrad. But like yeah, there's a 3-meter telescope in San Jose that you can use. You can apply for if you have an idea, just like do it. And they have spotters, or at least they did last time I was there.
Yeah. That was a huge deal 15 years ago, but
Yeah, they put you in like a little like telephone booth. You
Yeah.
can stay out there all night pretty much.
That's fun, but-
They bring coffee every once in a
Sounds
while.
like a bad gig.
no, but that's why, that's actually about the time that everybody started carrying the oxygen canisters because they had to be lucid while you're watching the laser.
Yeah, and it's cold and all that things. So yeah. Okay, so yeah, so over here is how, in part, Jen assesses the conditions for tonight. Matty has probably his own weather systems, which tell mostly he's interested in like wind speed and humidity. He doesn't just use this; he uses like a bunch of different sensors to make sure that it's not the humidity's well. You gotta be really careful with that. So yeah, so this is a kind of overlook of like what the basic conditions are tonight. So this is how we break it up here on the right hand side. These are plots that we use. It may be kind of hard for you guys to see, but on the y-axis here is attenuation in magnitudes. Let me see if I can make it bigger. It's back. That doesn't really work. Okay, so attenuation in magnitudes here. And we have these variants called CC. So CC is cloud cover, 50, 70, 80, and any. So we're currently in CC 50. This is actually from CFHT, and we don't technically use this except as like a kind of one of the data points. But this is photometric conditions. So so this is 50% best. So this is the like 50% mark or best, median or better cloud cover on Maunakea. CC 50 is photometric. So if you do the math, that means that 50% of the time on Mauna Kea, there's no clouds, zero, absolutely none. So that's part of the reason why it's the best observing site in the world. And CC70, this one here, so 70% of the time, it's better than 0.25 magnitudes of extinction. So you know your magnitudes, which I hope you all do. That's a good possible system. But I mean, that's only a factor of like 10% in flux density. So that's, I mean, it's not much. So 70% of the time, you're doing pretty good in terms of attenuation from clouds, Mauna Kea. Speaking of sharing data, this is the opacity tau at 225 gigahertz. This measures the amount of water vapor in the atmosphere. So this we have from SMA and JCMT. JCMT is the only one reporting tonight. But so currently there's a lot of water vapor in the atmosphere. So we're in water vapor any, which is just any amount of water vapor.
There is now.
Yeah.
Right.
Yeah. And we don't use that. Water vapor is only important for measurements in the K band. So at about 1.8 microns and redder. We are actually able to observe all the way up to about 6 microns. We actually had an instrument at one point that observed at 10 microns. We did at one point, but not anymore. So our reddest right now is 6 microns. And their water vapor kills you. So like you need dry conditions. Yeah. And so like, I don't know if y'all heard, but like the 30-meter telescope, that
Goes away, yeah.
and so that's a big deal. So it's not just that Mauna Kea is wonderful in terms of image quality, which we'll get to next, and cloud cover, but it's extremely dry generally. So even water vapor any is not that much water vapor. And then this one here is actually our measurements of the image quality, and these will be corrected to zenith. So
what are you now?
we are at
0.7.
0.75 in V band. Yeah. Yeah. That's about average. Yeah, exactly. So yeah, so that's 0.7 arc seconds in the visual band. Actually, these are RIZY. So right now, Jen's imaging in R, it looks like. So this is like this is roughly what we see as red. Yeah, roughly. And so this is corrected to zenith because, of course, if you take an observation, this is delivered image quality at the telescope. So like, what do we, an infinitesimally small source, like a star that is very large, but it's very far away. So it's sub-10 is a very small angle. This is the point spread function that we measure. So through the atmosphere, through all the optics of the telescope, through the optics of the instrument, because the instrument and the telescope are separate, this is what we measure on our detector, and then correct it to zenith. Because you can imagine if you look through a ton of atmosphere, it's going to blur out a star or a source much more than if you look through very little atmosphere looking straight up. And so our measurement, our kind of like metric figure, is image quality delivered at zenith. So this is like 0.76 at zenith. So you guys know what an arc second is?
Yeah.
Roughly?
1/3600th of a degree.
1/3600th of a degree. Do you guys have a feel of like how small or big that is? Like what's the degree on the sky? You guys know?
2 degrees is 1 finger.
Yeah. Basically. Yeah, 10. Shaka is 15 to 20, depending on your. Yeah. So one fingernail is roughly a degree. So 1/3600th of a fingernail is held at arm's length. So not like that, like that. And so that's an arc second. And then actually we have to track our
To a 10th or better.
requirement is better than a 10th of an arc second. So 1/36,000th of a fingernail held at arm's length. So you have this like 40-ton telescope on an 80-ton structure, and you got to track to better than like 1/36,000th of a fingernail all the time.
And the big radio telescopes, they were so well maintained, you could push them
Yeah.
with your hand.
Yeah.
Are you like that here or no?
No, I don't think you want to do that. There's a lot of voltage going through there. I don't know. Matty, have you ever pushed the dome? Or Jen?
What does the laser buy you in terms of seeing?
Oh, we can get to diffraction limit, more or less.
Do?
Yeah, close to it. Yeah. So we're depends on what band you're looking in, but
What's the fraction limit at R?
our
Right, so what is it? Lambda over D or 2D?
K, like a K band, it's like roughly 0.05, something like that. Yeah, we can get to sub 0.1. Yep. Yeah, we have two main modes. We have classical natural guide star adaptive optics, and we also have laser guide star adaptive optics, but we have a super seeing mode as well. So this is called LGS plus P1. We have a peripheral wavefront sensor. And we make the adaptive optic correction basically off axis. So if you're pointing at like a galaxy here, you have a 3 arc minute field of view where you can put this peripheral wavefront sensor on a bright star. And then you make the adaptive optic correction here. And so this sensor is not the same quality as our true adaptive optics system. So it, have you guys ever heard of a Shack-Hartman array? No? Okay. So it's a way of breaking up light from, I don't know, an object, and you have like multiple sensors on the detector. And so this peripheral wavefront sensor is a 2x2 Shack-Hartman, so it breaks it up into two. Our adaptive optics system, I don't know how many Shack-Hartman sensors it has, but probably 50 to 100. So it's much better than the peripheral wavefront sensor. So you can make a correction. It's not perfect, but you can get to like 0.2 to 0.3 arc second seeing pretty much anywhere on the sky. So we do the peripheral wavefront sensor does the tip tilt corrections, and then the higher order corrections come from the laser itself. So yeah, it's an awesome mode, and I love it because I am in charge of the near infrared part, and that's where adaptive optics pretty much happens, at least currently. Okay, so yeah, those are condition constraints. I'm going to take you into our observations. So Jen, are you guys still on the same target?
No, we just flew. We're setting up for a long split observation.
Okay. So this is actually like probably the
Trying to get a spectrum.
so I think we're moved on to a different program. Is that right?
Yeah, we moved on. We're acquiring on a long split program.
Okay.
So you're off the TOO.
We're off the TOO for now, I think.
Yeah, this is just a band one, a regular old band one program.
Okay. Yeah, I'll explain that terminology in a bit.
Now, band one is your ranking system, right?
That's right. Yeah.
How
So
many is it?
1 to 4 actually. So poor weather programs are something that we have, and so those are band 4, and those are actually like almost one of your conditions has to be set to any. So it could be either cloud cover any or image quality any, and then we take observations. So you really have, like, it has to be terrible out for you to call the night.
Okay, gotcha. But it's 1 through 4.
1 through 4, yeah. And our normal queue is 1 through 3, and then the poor weather, we actually consider that weather loss. So it's not technically science time, it's like bonus science time. Jen, which screen are you gacking on?
I am on
5?
5, but it's
5.
Yeah.
Okay, let me
Does it work the same with the cinnamon? I don't know.
No, I
it
think you
doesn't.
need to
So
go to, yeah.
yeah, I'll have to scroll over. Yeah.
Yeah.
So everybody
Sequence
avert their
pause.
eyes. No, I'm joking. Okay, so this is our acquisition procedure, and I'll explain in a second, but we can just watch for a sec. So this is like the most active time of the night usually, unless something goes wrong. So Jen just took an image of the field, and then we put this is a optical image.
What's it saying?
And this is a image then of the slit. So we move off the source and we take an image of the slit just to define the slit. So it's just to illuminate the slit. So we put in this is probably 1 arcsecond wide slit. Jen then uses the software to calculate offsets, and you can see up in the top left corner, maybe. Okay, probably you guys can't see it, but it says P and Q. So we have our own coordinate system. This is relative to the slit. So we have P, which is perpendicular to the slit, and Q, which is parallel to the major axis of the slit. So it calculates the offsets to put the slit right in the center, so we get the maximum amount of light from the source. She then sends these offsets to Matti. Matti then makes a slight adjustment on the telescope. So these are fractions of arcseconds. So the offset right now was 0.1 arcseconds in the perpendicular direction, 0.2 in the parallel direction. And nice shooting. So there's the source, and we take a through slit image always. Jen's now centering it up. It probably, okay, so it looks like it's just 0.05 arcseconds, 0.04 arcseconds off the center of the slit.
Yeah.
Our threshold is
That's good.
0.05.
It's a weird.
0.5.
And this is your science source?
This is the science source, yeah. Yeah. And so then which is your ISD on, Jen? Or I can bring in by the ISD too.
It's, yeah, the bottom left.
Okay, so this is our GMOS instrument status display.
Delightful buoy.
It's all 1980s like graphics. Blink, blink, blink,
That's
blink.
great.
So the light comes in from the top for the instrument, and then there's all these optical elements to the instrument. So right now you see the grating blinking. Probably you guys can't see that, but so we're putting in the grating, putting it at the tilt that is specified in the program. So this is a central wavelength of 750 nanometers, so pretty red. It's our R831 grating. We have a bunch of different grating. We have 3 different gratings in at a given time. 2 that are kind of constant and 1 that alternates. So now we're done setting up the grating, and the software will automatically start the observation. So I think we're probably exposing now. So before the grading, it was 0th order, so we were just letting the light directly through. Now we're dispersing out the observation, so we're taking a spectrum of the observation of the target. So so there we go. So well, this is kind of a funny one. So probably should not. Yeah, this is so this is something that shouldn't happen, actually. Jen, are you seeing what I'm seeing?
The blanking?
No, well, that's also, but the exposure
sequence?
time.
Yeah.
Oh, yeah.
Weird.
So our detectors are very cosmic ray sensitive. It's because they're very red sensitive. And so let me go to a different screen. So yeah, they collect a lot of cosmic rays. It's basically a cosmic ray bucket. And so we actually don't allow observations for more than 1200 seconds. So this one is 1500 and something. So I might pause right now and check out what's going on with this program.
Yeah.
By the way, guys, if you have any questions at any point, like, please feel free. This is completely open, so just feel free to ask me. Jen, which program is this? Sorry.
It's Q138. I'm putting in a QC note into the night log.
Okay.
1200 is the limit, right?
It is, yeah.
In this case, would you just need to split it into multiple exposures, or?
Yeah, and there's overhead, which you know very well, but like there's readout time. It costs time, and that's time that's charged to the program. So people will try to say, oh, let's just take it all in one go. It's fine. I don't want to deal with like the 2-minute, extra time to read it out twice.
If they did read the docs.
how to read the docs.
Well, you do, yes, that's always nice.
Can't let ChatGPT read them for you.
Okay. Yeah, so I'm not gonna say what I'm thinking, but this is so there's a structure in place. So we have two scientists that look for that either work for the observatory, or we have what's called NGOs. So we have National Gemini offices, and there's UH. We have 6 partner countries that that fund Gemini. Actually, I can go to this.
Look at the flags out front.
Yeah, you can look at the flags up, but you can also look at this here. Yeah, so we have Korea here, Canada, US, Brazil, Argentina, and Chile. On Hawaii. And so each one of these sites has a office where there's anywhere between 1 and 4 scientists, research scientists, that work with us. Part of their job, part of their salary is paid by Gemini. And they support us within our community. So they advocate for Gemini in their community. And then they also support us on scientific programs. And actually, like one of the instruments that we're using tonight, Igrans 2, that was contributed by a Korean space agency. So they built, it was, I think, the first time that they've ever built an instrument for an 8-meter class telescope. So they work with us on, so Canada is building an instrument right now called GearMoss. It's going to be our next generation instrument. The US, so University of Chicago built Maroon X. And we've had countless instruments from partner countries over the years. So they help us support the programs. We also have a staff member at Gemini that looks over these programs. So it has to filter through at least 2 people before we have it anywhere near the telescope. So we want to make sure we get it right, because every second on the telescope is precious. And so in a case like this might have been an oversight. But it's nice because it's actually the first time this program has been observed. This will be the first observation. And so what we'll do is we'll pause on this program after this, and we'll go back to the staff member will go back to the scientist and say, hey, I noticed, like maybe it wasn't set up optimally. You still have, looks like about 25 targets for the remainder of the semester. Maybe you should consider, and by maybe I mean you should definitely consider, and by definitely consider I mean you should change your program around a little bit. And so then the staff scientist will work with that scientist to set up the observations in an optimal way. So a lot of my job is supporting other people. You all right?
Yeah.
A lot of other people, their technical aspects of that. We have this observing tool, which is very complicated. It's very hard to understand. It has all these different subcomponents, and it has, a lot of times people are setting up for like multiple different instruments. And so you need to know GMOS, you need to know G-nears, you need to know optical near infrared, you need to know, if you want to set up adaptive optics, you need to know something about adaptive optics. And that's not something generally a lot of people know about. So so we help them with that because we're trained in understanding this. So let's go back to our screen. TSD is on 1, Jen, is that right?
Yeah, and sorry about earlier, I thought you were asking about the TSC, not the IFC, but yeah, it's the bottom left.
Okay, well, thanks. Okay, so so this is our telescope status display. This is a lot of information, but this is a side view of our telescope here. And so the basic structure is light comes in, it bounces off the primary mirror down here. Secondary mirror goes into this Cassegrain structure. We call it instrument support structure. And then there's a bunch of different ports for the different instruments. And so Igrans 2 is on port 3 here. GMOS, which the light is being piped there right now, is on port 5. We have AO on port 4. We have our Gemini calibration environment on port 2. And then we have our visitor instrument. In this case, it's Maroon X, which is like it's a contributed instrument. So it's partially visitor now, but we're adopting it. So we're adopting it as a facility instrument pretty soon. So it's so popular that we're gonna keep it.
Into a real tool.
Aw.
Have a little party.
It makes nice rainbows. So yeah. So this is our tertiary mirror. This is what we lovingly call the science fold, and this redirects the light from the telescope into the different instruments. And so this is the thing that turns. This I was a little bit worried about the precision of the movement of this thing at one point, because we take observations where we kind of like flip to the calibration environment and then we flip back to the sky. And I thought, oh, you know what? Maybe when we have a really small field of view, maybe that's not a great thing. Maybe the precision is not that great. It's better than 100th of an arc second, probably. It was better than my measurement capability. So it's like it's solid, and I don't know how they get the kind of mechanical precision, but it's amazing. I don't know. It never ceases to amaze me. So anyway, so yeah, so the light pipes into GMOS, and then it goes into this tiny 1 arc second slit, and then it goes through the grating, and then it's dispersed. And in, I don't know, let's say 15 minutes, the science observation is going to be finished, and then we have to take calibrations right at the location of the object, so where the telescope is pointed at that time, because gravitational flexure exists, and so that can actually change where the trace, where the signal is on the detector. So if we point, low on the ground, an object might appear in one part of the detector, and if we point straight up, that's a different vector, gravitational vector, and so that will change where it's on the detector. So we want to do flat fielding, and we want to do arc lamps at the point in the sky that we're observing, basically.
The calibration is in one of the slots.
That's right.
Is it
Yeah.
the same, like calibrations for all the different instruments, or?
The calibration environment is the same, but no, I can actually bring up the.
It's much more nimble than Subaru.
Oh, it's okay. It doesn't like this. Let me see if I can bring it up this way.
For reference, PFS and HSC on Subaru are mounted on the top of the telescope, and they have to physically take that off and replace it to swap instruments. So that takes much longer than moving it in this case.
Yeah, right. Yeah, I mean, like the Hyper Supreme cam, the filter movement is 20 minutes.
Yeah.
I mean, but they're like 5 ton. I don't know what they are, like 2 ton, 5 ton
That's
filters.
because it's a huge filter.
Yeah.
And so
They wanna
like
move it really slowly.
no knock, because it's 1 square degree roughly field of view. Our biggest imager is GMOS, which is 5 by basically 6 by 6 arc minutes. So I mean, one.
Subaru and Gemini are opposites.
Yep. Yeah.
Wide field's the best in the world, and probably small field, narrow field.
Yeah.
Best in the world.
The quick, yeah. And they both have like it depends on your science, because I mean science is so varied. There's so much, like no matter how diversified our capabilities become, like there's always somebody that's like finds some cool science case that like randomly pushes the edge of like one of our capabilities. So it's neat. Like yeah, they both have their pluses and minuses. So these are all our lamps. So we have a quartz halogen lamp, we have an argon lamp, xenon, thorium argon, and copper argon. And so depending on the wavelength, we change the exposure time, we change the elements that we illuminate. We have shutters. So for example, like in the K band at 2 microns, it's actually mostly heat. So you can just like close the shutter and you can just take a heat spectrum. But we have what's called cross dispersed spectra. So in the near infrared, you can actually take a grating and a prism and put them together in a path, and it'll disperse one way and then the other way. And so GNIRS is like one of the world's best instruments at this. And so you get simultaneous observations all the way from 1 micron to 2.6 microns spectrum. And so okay, for those calibrations, we actually have to take lamp off, lamp on, shutter closed, shutter open flats, because in the in the shorter wavelengths, we need the lamp to illuminate things, but the lamp doesn't do anything really for the longer wavelengths. So then we close the shutter and just get a picture of the shutter. So so you stitch these two together to make a full flat. Have you guys seen like flat frames and arc frames before? No? Okay. So yeah, I mean, you get your science exposure. It'll be like, let's see.
But your wavelength calibration does it depend on elevation and
Does.
all that mess?
Yeah, unless you have a flexure compensation system,
Okay, so
which like,
it's-
yeah, so like Demos on Keck, that instrument was the first, I think, ever on the planet that had a flexure computation system. That was 2003 that they developed that. Santa Cruz actually, and Mossfire is another one that has that's a Keck instrument that has a flexure computation system. None of our instruments have flexure computation. We have atmospheric dispersion computation, so Maroon X has an atmospheric dispersion corrector. LRES on Keck has an atmospheric dispersion corrector. These are usually when you have like long wavelength baseline observations. So like LRES goes all the way from the blue to the red in the optical, and so you don't want to be like losing flux. Yeah, there's all sorts of things that we can talk about.
For tech and stuff, you can take calibrations at the start of the night or at the end of the night, but it doesn't have to be exactly right after you took your science observations.
Yeah.
Because the FCS, in theory, fixes that for you.
That's right. Yeah, yeah. And I grew up on Demo, so it was like I was spoiled because yeah, you really don't. You take your like you could even take your arcs and flats from like
that's what I-
3 years ago
Yeah.
and just be like, all right, fine. You throw over the calibration. It's probably fine. So yeah. And here, yeah, we have a obligation to take them every hour to hour and a half, depending on exactly what the observations are. But actually, one of the things that they don't do at Keck, which we do here, is take telluric standards. Have you guys heard of tellurics before? No? Okay. So there's telluric bands in the atmosphere which absorb light. So if you look in the near infrared, you get like tons of emissions, usually from OH lines, but there's also like water vapor and stuff. And then you have these bands where you have absorption of light. So you have some combination of emission and absorption. And anytime you're taking an astronomical observation, of course, you want to get to the intrinsic properties of the source. You don't want to like get a bunch of atmosphere or optics or whatever. So you have to remove all of those things. And one of the things that's really important to remove in the near infrared is telluric absorption in the atmosphere. Because imagine like you're taking a galaxy spectrum and you see absorption of like calcium features, and you're like, aha, like that's that strong. And so I know that means that galaxy is 3 billion years old on average. Like the mass weighted age of all the stars in that galaxy are 3 billion years old. And I'm pretty confident about that. And then it turns out that there's telluric absorption from the atmosphere right at those locations. Well, you've just made the absorption deeper than it actually is in the galaxy. And so you've biased your results to give you an answer which is basically older than what it truly is. And that's not good science. You don't want to do that. So don't do that. And so telluric stars are actually like, they're usually A stars. So like Vega, it's like, you guys know how like the stellar classification scheme?
Yeah.
No, you do.
Well,
Everybody does though. Like it's like one like everything in astronomy. It's kind of just like entrenched from the past and like doesn't really make a whole lot of sense, but it's that way for funny reasons. So yeah, so A stars are the ones. Anybody remember like what's special about A stars?
That where the hydrogen lines fade out or get strongest.
The strongest, yeah, exactly. So it goes down the alphabet and like how strong the hydrogen features are. Yeah. So it's like, it's just a random thing. It used to be that people thought that correlated with something, but it doesn't really. It's just what's good for hydrogen. So our sun is a G star. So that's a little bit cooler than an A star. B stars are a little bit hotter than A stars, and then O stars are like the really, really hot ones. So O stars are like 30,000 Kelvin. A stars are like in the neighborhood of 8 to 10,000 Kelvin. And then like our sun is like 5,600 Kelvin at the photosphere. And so A stars have these very regular features. So if you look at like M dwarfs, these are like really cool stars. These are some of the most common stars in the universe besides like subdwarfs, like R and T. But so M stars are like a tenth of the mass of like 10th solar mass, 0.3 or something like that. And they have such complex chemistry in their atmospheres that like there's all sorts of crazy absorptions, and so you can't really model that out. But A stars are like super regular, and so what you can do is you can take a template of that star. You say, okay, I know there's this like A class, and then there's like a temperature classes within them. So like A 0 to 9. So 0 is the hottest, 9 is the least hot within those classes. And then you say, okay, that's whatever, that's 8,271 Kelvin. I throw my model at it. I have surface gravity. So there's a Roman numeral after that, which B is a main sequence star. So A0B or A3B or whatever. And you have a model of that. And the model is usually really good relative to the observation. So you take an observation, you know what it should look like. You then divide the model basically into the spectrum that you observe, and the quotient gives you the response correction. Does that make sense? Yep. So then you just apply that to your science data. But the atmosphere in the near infrared changes on the order of minutes. And so like in BFS, the sky subtraction in the near infrared is not great because we take 15-minute exposures. And so when you take two observations, the sky is so bright in the IR that you have to do basically difference imaging or difference spectroscopy. And so you move things around. It's a little bit different in PFS because you have calibrators, but the sky changes. It's very dynamic. And so we take telluric observation, the maximum amount of time, temporal difference, the delta T in between the science observation and the telluric is an hour and a half. So we will take these throughout the entire night. And this is something like Mossfire you never do on almost. You could like pretend to put one on your mask, but it's not usually that great. And it probably was just some random thing that you stuck on. So yeah. So that's one of like the many calibrations that we do. So the arc and flat spectra. So as soon as the science spectra is done, Jen, how much longer do you guys have on the exposure?
5 minutes.
About just under, no, probably about 5 minutes, maybe a little bit.
Okay. Okay, cool. So in 5 minutes, we'll go back to the screen that'll show the spectrum. And so it's R831. So it'll probably disperse from like 500 nanometers to like 1 micron, something like that. And so, of course, the calibrations have to go all the way from across that range. So we keep everything the same in the optics of the instrument. And then we just shift the tertiary mirror over. So we pipe out light from here, in this Gemini calibration environment. It'll hit the science fold. The science fold will turn to be horizontal in this picture. And then it'll enter into GMOS. And so it'll illuminate first probably the quartz halogen lamp, make a flat field. And a flat field is just a response function of the instrument optics to a flat source. So there's vignetting and all sorts of things that happen that are nasty. And so you got to remove that. Yeah, exactly. Yeah. Somebody drops a cup of coffee on it. Yeah.
That's better than dropping a wrench on your mirror.
For example, yeah. But,
That is a good example to bring out.
I will say it's maybe dropping a wrench is equal to running your primary mirror into an earthquake strut.
Oh, that's yes. You were
We can
down.
just edit all that out, Jamaica. That'd be cool.
I got,
We're not race to the bottom here.
yeah, no worry.
Yeah, but I mean, yeah. So I mean, anyways, optics are imperfect, right? So and instruments are imperfect, and quantum efficiency is not equal over the entire detector. So so you gotta take that into account.
Do you want to say how long you were down due to the cyber attack?
Cyber attack was about 2 months, I think. Is that right? Like,
Wow.
Jen, Matty, I don't know.
Yeah, she was in my office afterwards, and that was after.
Yeah. It's.
I think it was around 2 months, a little bit more.
It was. Yes.
It was terrible. Yeah.
Was that last year or the year before last?
Yeah, last year.
23, right? July 5th of 23 or something like that.
Yeah, that
Yeah.
sounds right, because it was right before I got here, and yeah.
I remember I had my like research group meeting here for a week, and we got through Monday, and we were like,
Sorry to bring this up. but
yeah, no. I remember it was actually fun because, well, it was fun for us at the time because, so I was in this room with my research group. I have a research group of like 12 scientists, and they came here, and we were like, yeah, it's fun. All right, like let's talk about protoclusters and stuff. And then we got cyber attacked that night, and Matthew was actually on the telescope, right? Jen, were you on, or I know Matthew was.
It was
Matthew
me
and
with
Sunny?
Sunny.
Yeah. Okay.
Yes.
And
Sometimes.
yeah, a lot of weird things started happening from what I remember.
It affected both hemispheres, right? It was, I'm sorry.
A lot less Gemini South and the mid-scale observatories, but they got hit. But we were the center of it. Matty, how do you know you get cyber attacked?
Everything started with problems, network problems to get into internet. And I remember SecExec webpage start to stale. It wasn't updating. And suddenly we figured it out kind of at the same time with Sunny, and suddenly we started losing a lot of subsystems of the telescope that weren't related. That was crazy because usually if you have a fault, you can see like a tree of faults. You know where is the issue at least, but this was something completely different. Can you hear us?
Yeah. I'm just gonna close this.
Okay. So the thing is that multiple subsystems that are not related started to fail, and we didn't know what was going on, and we lost communication with the telescope. So we were kind of blind regarding the status of everything from here remotely. So we started calling people, and we couldn't even call because the phones were down too.
Everything was off.
And it was very complicated. Actually, I think it was on my first solo shift. I'm glad I was with Sunny.
Yeah, you were pretty
Who
new.
is more experienced, has more experience. I was not uncomfortable, but it was very weird. So we decided to park the telescope and start calling people with our own cell phones. And Sunny suspected that something happened at Gemini South because it was already day. I think it was around 4 a.m. or so, 3 something. And we parked the telescope. We tried to play it safe, and I'm glad it worked. We figured it out that the telescope and the dome was parked, but a lot of subsystems kept in error state. I'm glad we were able to park everything. That was the main thing. And we went to sleep around 5 a.m. without knowing what was going on. And worst part is that people was trying to help us and reach out to us, but we didn't have cell phones or anything, not even internet. So it was difficult to figure it out what was going on. And during the next day, we have a better idea that we were cyber attacked and stuff.
Not
It was
just a town power
terrifying.
line. Yeah.
Yep. Yeah. It was brilliant. And I mean, we got back on Sky. All the effort was put to get back on Sky as soon as possible, like to get the telescope operating. But I mean, we're still dealing with the residuals of the cyber attack. We still have subsystems that are down.
So you're less vulnerable now?
Oh yeah, yeah. Like these machines here in the operations room, they're basically walled off from the outside internet. Yeah, they can't be touched, more or less. So Jen's actually showing us now. So the tertiary just shifted, and we're in the calibration environment. So this is the science frame. The previous one that she was showing is a science frame, and this is an arc frame, and this is a flat frame.
Please move to 320.
Yes.
I'll go back to the science. I just needed to check the data. There you go.
Thanks, Jen.
320? All right.
Where's the bathroom?
bathroom's just down the left and first left.
Thank you.
Can you extract and do a 1D on the fly or?
Yeah. So we actually have a Dragons environment that's running. So this is the Gemini Python-based data reduction. And so you have like QAP up and running, Jen?
Yeah, it's on the bottom right monitor.
Bottom right. Okay. Yeah. So so just to explain, this is a static screen that Jen's showing us now, or that's one way. Yeah. So so this is
One more over.
okay.
the
So this is a 2D spectra here. And then so I can go over here. Yeah. So so the skylines are the things that you're seeing in the vertical direction. The horizontal direction is the dispersion axis. So so spatial is up down, wavelength is left right. And blue in this case is it's flipped relative to the other image. Blue is to the left, red is to the right. And for people that have observed a lot, that'll be obvious here because skylines are a lot more in the right. Exactly, yeah.
So are you doing on, off and such for the observations for the?
This particular program is not. Generally, I would suggest, yeah, you do both a spatial dither and a wavelength dither. So we have gaps in between our 3 detectors there. So you want to dither the wavelength over so you get a continuous spectrum. So when you stack it together, you get a continuous spectrum. And then, yeah, if there's any defects, making a movement in the major axis dimension is important. So yeah, there's a reduction going on right now. It's identified the trace. Do you have the spectral software up? The spectral quality assessment, Jen?
Sorry, what, Brian?
Do you have the spectral QAP up, like the web page based?
Oh, this is it. Oh, the spectral one. No.
Yeah.
Hold on. I'm just getting fed up. Hold, give me one
Yeah.
second.
No, take your time. But yeah, it's actually running reduction in the background. So it takes those arc observations. So those arcs is that's just from an elemental lamp. So the wavelengths are known. And so you're mapping X and Y location, mostly X, to wavelength, though there you can see that there's some change as a function of Y. And then so this reduction software flat fields, it takes the arcs, it maps wavelengths to X, Y locations. And then it extracts the spectrum. And so it's identified, looks like 9 different places where there is potentially a spectrum. This is at 1068. I guess that's probably in the center. So that's probably the target of interest. So it's not like a fully response corrected. I mean, this is just an on the fly reduction, but that's a 1D spectra. So that's just intensity, flux density, versus wavelength.
Are those jumps real or is that somehow how the filter's broken up?
That looks real. I don't know why, and it could be like that the extraction is too narrow or something like that. But yeah, that
The 2 breaks, is that between the detectors?
there are 2 breaks between the detectors, but actually it interpolates pretty well. So that break is at 760 nanometers, and it looks. I don't know what kind of source this is.
What kind of sort?
Look kind of bright, didn't it?
It's a star.
Nebula or something or a star?
Star, yeah. I don't know. Yeah, that break I've never. 760 is
2 breaks going the other way.
telluric A feature, maybe the A band. So maybe some telluric features are helping that out, but yeah, not totally sure. And then so on the left there, now we're doing another acquisition. Jen's doing another acquisition. And so it's identifying all point sources in the image, and it's then doing a reduction and measuring the full width at max. So this nighttime QA metrics, the first tab, it'll actually report for every image that we take what the image quality is at that location and what variant that is. So you can see it running in the background down there at the bottom left.
Sorry, what's the A band? Because I've only heard of like the crazy band. Deeper.
Okay, so it's a telluric band in the optical. So there's A band and B band, and A band is the stronger of the two. And I used to know the wavelengths by heart. I think. Do you know them? No. It's 7,500 angstrom, something like that. And so it has this like very typical telluric shape, which is like a deep absorption at first, and then it's like a series of absorptions that get consecutively shallower. And so this is also something you can model out, and it's dependent on air mass. So the more atmosphere you look through, the more absorption is. So that's not like a band, like G band, like, yeah, Grizzly, right, exactly. It's not that, it's a telluric band.
Oh.
Yeah.
So two of them.
Yeah, go for it. This is what Shadow's for, is random
Where
questions.
is espresso located?
For what?
Espresso.
Espresso, the instrument? I think it's VLT. Is that right? I don't know.
Question?
Espresso, the instrument Espresso?
Oh.
I've heard of it before. I'm not sure if it's on VLT or if it's on like LBT. What type of instrument is it?
I'm not sure. Okay, I'm just remembering because I remember when we did some radio velocity stuff. I used some espresso.
Right. It is a high resolution
I
spectrograph.
don't know where it's from. I'm just curious.
My guess is VLT because I think it's it has to be backed by a decent amount of glass to be that powerful. So it probably needs 8 years and there's not that many emitter telescopes in the world. My guess.
Last third question. For not specifically for Keck, but like what instrument would a coronagraph go hand in hand with?
Chronograph. So we're planning on getting, so our next instrument is called GPI 2. This is Gemini Planet Imager 2. We like series at Gemini, so we have a lot like Igrins too. And so that is like an extreme AO planet imager. And so like some of the first direct images of planets were taken by Keck with, not sure what instrument.
I was trying to think myself, but
I don't remember which instrument. And then GPI, the original planet imager for Gemini. And so you stick a chronograph over, and then you just observe, like, it's the same type of thing where you observe like once a night for, an hour for over a baseline of years usually. And so then you can build up these images of planets orbiting around their host stars. So that's a pretty normal.
It's my favorite thing when somebody posts that one GIF and I'm like, I know the observatory that made that.
Yeah, it's a combination of Keck and Gemini. Cool. Yeah.
760 and 687, by the way.
The
Bands. A 760. B
760. Oh, okay. Okay. Yeah, so that was probably telluric. Yeah. You guys have other random questions?
Sort of a general question. So there's the two telescopes.
Yep.
I was wondering, like, I guess how you guys interact like throughout the night, or they're totally separate queues, I'm assuming.
Kind of. There's a lot of crosstalk between the
Okay.
programs. Yeah. So we have a lot of PIs that have, especially target of opportunity PIs that have programs in both hemispheres. So of course,
You don't know where it might
you don't know where it's going to
go.
go. Yeah. I mean, if you're looking at LIGO targets, then probably in the north, right? But yeah. So yeah, the staff work very closely together. We don't like generally overlap in terms of like functional work. So they have their instruments and they work on their instruments, but we all use like kind of the same software. So, and we share like policies and calibration sets, and a lot of the subsystems are near identical, if not identical. It's very common for science operations specialists. So Matthew actually started at Gemini South because, well, he didn't have a visa to come to the U.S. So he started his training at Gemini South, and then came here. And Jen was recently down at Gemini South, like maybe what, 6 months ago or so, Jen?
Like a few years ago now, but I've been 3 times.
That was a few years ago, really? Oh my God.
I think it was, what year did you move here, Matthias?
2022.
Okay, so it was 2023
Yeah.
that I went.
Holy
and
crud. Wow, I remember that. Like, not
and
that
I
long
was
ago.
there in 2018 and 2019 as well.
So people can kind of swap out.
Yeah, yeah, and it's like cross training. Jen, like the last time you went, what was the? I mean, I know you observed, but what else did you do down there?
Yeah, that was actually during our mirror incident, and I ended up going out there because I'm the SOS lead on our new instrument Igrants 2. So I went out there to learn how to use
Okay.
Igrants. And then the time before that, I was working with a collaborator, and the time before that, I was training to be the ITAC technical secretary. So I was out there for
Cool,
like
yeah.
5 weeks for that one.
Yeah. Yeah, so usually having a reason to go down there is important, but like, yeah, we share a lot of stuff. And so like the last thing that Jen mentioned is our international time allocation committee. So we have national time allocation, super.
Not to be specific, right?
And so, yeah, so we have our like national time allocation committee, and they rank all the proposals that come in through that channel. And then we have an international time allocation committee that compiles everything together. And so that at that point, there's a lot of like crosstalk between Gemini South, Gemini North. We coordinate shutdowns, so we don't want to be like both of us off sky at the same time. We actually, like, if they're in, like, let's say GMOS in the south, we have GMOS South as well as GMOS North, and it's basically an identical instrument module with a few subtleties. Let's say GMOS South goes down, like they have a, I don't know, cold head issue or something like that. So they have to do some work on it. It's not, they can't get the parts, it's not gonna be replaced for 2 weeks. We would absorb probably some of their programs and take observations that are equatorial that we could see here at a reasonable air mass. Also, like the mass making machine. So we do multi-object spectroscopy. The mass making machine is here in the north. It's unfortunately currently broken. But when it's working, which is most of the time, so like Matty and Jen during the day, when they're not on night duty, they will mill masks. So we have a laser
it's a
cutter.
physical
It's
mask.
literally just, yeah, over there. It's carbon fiber. And yeah, exactly, yeah. And what's it? F2 masks are aluminum, is that right?
Yeah.
Probably, that's what
Yeah.
Mo said.
Yeah.
Yeah,
Yeah,
I
and
have
we've
a lot
got
of
SOAR
deals.
masks as well.
SOAR masks, that's right, yeah.
Also, the future software is gonna, you don't apply for Gemini North or Gemini South specifically. So the software will determine where you will get your observations again.
Right,
In the
yeah,
future.
right. Yeah, so it'll check the Q, the pressure factors, like the right ascension pressure factors. So yeah, I mean, a lot of this right now is done by humans, and it's because we're generally pretty good at it. And we've been trying to create models that work as good as humans. We haven't been able to do that yet, but it's coming. And some of the software is going to do some of this calculus for us. So we have like the Q coordinator right now, which is a staff member. We all rotate out. So like my job, like I'll do research for 2 weeks, and then I'm the instrument scientist for juniors. So if anything goes wrong with we were just like rebuilding it from scratch basically. It's a 20-year-old instrument, so it had some creaking and groaning. And so I'll like go up to the summit and watch people that know actually what they're doing do their thing. And I'll plan the queue, I'll observe at nighttime, so I'll take what Jen's role is. So there's a queue coordinator, and the job is so intense that it's you only do it for a week at a time. And you're on call 24 hours a day, so you never can have your phone off. Like I've gone like camping before at like Kapa'a on the other side of the island when I was on queue coordinator, and I had to bring my laptop with me, a hotspot there, because I got called at 5 in the morning, and it was like, okay, I need to be ready to go. So that the software is designed to replace at least part of that. So it recalculates the plan like every hour or so, if like given the conditions, and if you happen to, if a telescope subsystem went down and you couldn't observe that last observation for an hour, it will recalculate everything and they'll say, no, here's the most optimal plan. It's not fully tested yet, and the tests that have been run so far I'm not like super optimistic about, but it's getting there. It's getting better by the day. So that's the plan. And yeah, so it's all teamwork. Like Jen and Matti are there at nighttime, but we have 160 staff across the two sites that work, and day crew is a big part of that. So having everything ready in the daytime, good to go. All the subsystems good to go. When we get there at nighttime, that we're hitting the ground running. We do not want to waste a second of telescope time. So yeah. Let's see. So I had like a random set of facts about Gemini, but I think I'll not go over those and just see like, are like, yeah, what are you guys planning on like flying the telescopes as your work? Like, Charlie, I know like you are working on data that's already been taken, but is it something in your future that you want to like propose for telescope time?
Yeah, probably. We'll see.
Yeah, you'll see. Depends if you stay with astronomy or not.
Yeah, well, I'm want to, but in applying data science too.
Yeah,
without
yeah,
Getting into a PhD.
yeah.
Yeah.
I mean, a lot of our problems are like heuristic problems, like data science problems. So, yeah,
Okay, perfect.
there's a future, yeah. But yeah, I mean, like here, I could talk a little bit about we're gonna stop probably in about 20 minutes, but I could talk a little bit about the Q system and like what the process of a proposal is. So how many people have submitted a proposal, or like, I guess for Champ, did you have to submit a proposal? No?
No, mine was all theory, so.
Okay, all right, but you submitted like a proposal for Champ, like just in general, like I
Like
was.
to apply to chair?
Yeah,
No,
exactly.
I sent an email that said, hey, I'm interested in.
Oh, really? Okay, okay, all right.
Probably is the timeline.
They've submitted applications
Okay,
to
so
things.
letter.
Yeah, I have submitted applications.
Letter of interest, yeah, okay, got it.
Brian, you know it takes a year to get done and on a telescope.
No, not a Gemini, so that's, yeah, so like, yeah, so anyways,
You're unique in that sense.
we're very flexible, so yeah, like one of the things that we do here, let me go down to this.
Yeah, you should explain that. That would give people hope.
So this is how,
We actually have people who can game the system.
letted that up. So normally, well, okay, science is mostly getting told that you're wrong. That's what science is. And like, proposals, like, as Dave mentioned, there's oversubscription. For every 10 people that want to get time on Gemini, there's one person that gets time on Gemini. Depends on which TAC you go through, time allocation committee you go through and everything, but it's roughly like somewhere between 10 to 1 and 4 to 1. So it's hard to get time on a telescope. And as Dave mentioned, also it's usually like you propose, you wait 3 months or 2 months, depending on which institution you're at, and you hear back and told your idea is terrible, and then you 6 months later and you keep doing it, and then finally, yay, you get time on the telescope, that's great. Okay, and then you wait and you wait and you wait and you wait.
Get weathered out, yeah.
And then you get to the telescope, you're like, yes, I flew to Hawaii, like, yay, I'm here and everything.
That's why the Q is good. I mean.
Yeah, so there's some downsides definitely, but yeah, I grew up on classical observing. I love it because you're basically God for the night. You can change your observing plan. You can go to different targets if you want to, and nobody's there to say no unless you're going to break the telescope or the instrument. And so Q is a bit more rigid in the sense that you have a set of targets defined, and kind of everything is defined ahead of time, or the kind of class of scientific observation is defined ahead of time. And you have to get approval from our head of science operations which we also rotate out. So yesterday I was head of science operations. Today I'm nobody. So yesterday I had God power over all the Q programs. Today I don't. And so yeah, so you wait. Okay, you get the telescope, yay, and it's cloudy, and it's foggy, and that sucks, and you have to reapply the next year, and then you're told your idea is terrible, and then you're like, wait, but you guys liked it last time. No, now it's terrible. And so you go through that process again. And so this is where the queue is really awesome, is because you have the chance every single night to get an observation, and it's you know, we might take only 50% of your program, but if you got 50% of your targets, maybe you're happy. Like maybe that's enough to do your science, and you're not going to say, well, no, I can't do my science. I need all of them. You're going to try to do your science anyways. But one of the really cool programs that we have is called Fast Turnaround, and this is really neat. So I work on the Fast Turnaround team, and it's every month. So every month you can get told your idea is terrible.
Hey, that sounds great.
By your peers, because it's called distributed review.
Yeah, it's reviewed by our quick committee.
Exactly. So it's all your competitors basically that are reviewing you, and you're reviewing your.
Are you unique in that, Gemini?
Fast turnaround? Yeah. So it's no joke. It's fast. So you get the proposals, all the proposals that you need to review on the first of the month. So you have to submit by the last day of the previous month.
12 times a year. Yeah.
Yep. And it's only certain partner institutions that can do this, but yeah, but it's vast majority of people can do it. And so you get all the proposals that you review on the first of the month. By the 15th of the month, that process is locked out. By the 22nd of the month, everybody who gets time is told they have time. And by the next day, if your contact scientist like me is very nice, then you can get your program set up and you get data taken. So from the time you propose to the time the first photons can come in could be 3 weeks. And you can do this every single month. And
Great.
yeah, and so we award about 15 hours per month per site for this. And so it can't be like a huge program, but it doesn't have to be like, this is the most revolutionary thing ever. It doesn't even have to be like super timely, like we have to get it now. It's just, this is a good idea. I would love to have 2 hours of telescope time to do it. Is that?
And do you partition it by partner? In other words,
Yes, yeah.
yeah, so you're applying for the fast turnaround for the 15% of the telescope that we get time on, for example.
Yep. But anybody from the US can apply, and the US has the 60%. Yeah, but anywhere in the US is actually up to, yeah. So 60% of the time is the US's time. So it's, it's substantial, and that's aggregated per semester. So it's not like for a given month that it has to be distributed in that way. So we also have like director's discretionary time, which you can just basically write to the director and say, hey, this is like a super awesome idea, but we ask that you publish within like 6 months. So it has to be like, bam, it's really exciting. We have poor weather, which I mentioned earlier. So this we call band 4, and it's basically like, we were going to be kind of closed. We're not doing very much anyways because the weather's just so bad. So give me some bright targets that we can look at that you can do science with. We have large and long programs that go over like anywhere from like 4 to 8 semesters. So it could be like hundreds of hours of telescope time, and then regular programs, which are once per semester. And so, yeah, there's distributed review, there's time allocation review. One of the things that we've instituted now for all of our partner countries as of this semester is dual anonymous review process. So you're not allowed to reveal who you are. And of course, the people that are reviewing don't reveal. And this has, I think we have a slide somewhere here.
That's interesting. I didn't know you were doing that.
Yeah. So it's about unconscious bias.
What you're saying is, yeah, exactly. But is it dual anonymous review?
Yep. Yeah.
Oh.
So here's one of the slides that we have for this.
So who wins in this?
Non-R1 institutions.
Wow.
So this is pre, they call it DAPR, but DARP.
That's amazing.
So dual anonymous peer review. This is other academic institutions. So R1, R2, like UC Riverside is an R1 institution. University of Hawaii is R1. It's research center.
Research institution.
And other academic institutions like liberal arts institutions before dual anonymous, 7% of the success rate after 17%. So there's obviously built-in unconscious bias, and this goes for gender. This goes for a lot of things. This goes, and also because we have a lot of partners where English is not the first language, we push very hard for people to not take grammar as like, like, oh, they couldn't construct a cogent sentence in, like proper grammatical ways, so therefore their science is crap. That we really try to make sure that people evaluate the science. And if we see any comments on the process about that, we actually let the reviewer know that's not what you're supposed to be reviewing on. So that's really important to us.
When should I start writing these proposals?
Anytime. Yeah, so fast turnaround, again, it happens, I mean, it's the last day of the month, every month. So anytime you want. And so another thing that I would mention is, like, let's say you become a professor and you want to do like a National Science Foundation grant. AAG, yeah, let's suppose, Dave, that you want to do this. I also did this. I had to give this up because I came to work for an institution. So I've proposed for these before successfully. They're 150 pages with a lot of budget stuff and a lot of this and that. And it comes with money and it's important, but it's a big pain in the butt. And you have to start like 3 months, 5 months, depends on how good your administrative people are. You have to start a long ways out, and you have to think, very comprehensively about, your idea. We have one page for scientific, to make your case. And in
fast turnaround.
Nope, for everything.
Oh,
Yep. So it's for the scientific justification, it's one page. Even long and large programs are different, but for regular semester, director's discretionary and fast turnaround, it's one page. So make your case, tell me why the science is good, make it broad, because it's, it's people reviewing that do solar system science for your high redshift galaxy, or vice versa, right? And so you have about a paragraph to like contextualize, paragraph to like get into the details without going too far, and then basically you're done. and then your figures do a lot of heavy lifting. So we do 2 pages of figures and references. So make your figures really good. And then the technical justification is a page. So that's the basic layout of a
references are extra.
there, yeah, within the figures. Yeah. So it's 2 pages of that. So that's another thing I really like about Gemini, because
So 4 or 5 page packet total.
yeah. So yeah, like a CAC proposal through like UC or UH, I mean, it's going to be 4 pages.
Yeah, we have a max limit for,
Up to 4.
and you're putting like 3 telescopes in a single proposal.
right,
You
yeah.
can't go over 5 pages.
How does the UH TAC interface with, is it just a separate channel, or is it,
From US.
or I guess from the rest of the
We do our own reviews.
reviews?
Yeah.
Our own.
So then that feeds into the ITAC, and then that's all matrixed together. So
Well, your TAC sounds a lot less biased than our TAC.
Yeah, we have.
everybody knows everybody there, right? So
Well,
that's
that's good. and
Kind of
bad.
impossible to double.
yeah, right, yeah. So at the US level, that's, they're receiving hundreds of proposals from all over the world, so that, they don't know. Yeah, so it's a very live proposal process. It doesn't take a lot to submit. Actually, I have a program this semester, and I was like, at the semester interface, I was like, I don't know if I have like the time or energy. I was like, oh, come on, it's a page. And so I wrote the page, and then I submitted it just on a whim and got the time. So it's nice in that way. And you can keep trying if you want just a couple hours of telescope time, you can keep trying every month, and it's no problem.
Find a friend who's written one before and run yours by them. Yeah. That's the way you do it. That's the way you get started.
Yeah, and actually, as everybody here is a research scientist. So like all the contact scientists, the instrument scientists, we're all researchers. So we all have proposals. So if you were like cold email us at Gemini, like, hey, like, could you share a proposal with me? Like anybody from the contact scientist group could share like a successful proposal to Gemini or other telescopes. So that's no problem. Yeah. So yeah, we have about a couple minutes left. You guys have any other questions? Maybe we can check in and see what's going on the telescope.
Is there any major thing in the future we should know about Gemini, or? You're not gonna have a name change? We heard PFS is getting a Hawaiian name.
Oh, is it really? Oh, that's great.
Just
You're
heard
the
that
first to
this
know,
morning.
other than us.
Okay.
Well, we don't know what it is yet.
We
but
don't know what
that
the name
it
is.
Yeah.
It is being named.
Yeah.
PFS doesn't sound all that fancy, so.
And everyone always confuses it with PSF too.
Yeah, exactly.
They do. Yeah, that's true.
So do you have new instruments coming, or?
Yeah. So actually, so Igrons 2 is just fully commissioned as of this semester. Well, I guess last semester. And that we actually wanted to give the name Iiwi. So the honeysucker bird. But
Or just, it's Alex's newfound profession.
It's been, yeah, someone.
but the software people complained that Okina was hard.
It is,
Alright.
yes.
Yeah.
Care maps won't often have it.
Figure it out.
So yeah, understandable. But yeah, so that was partially why that didn't happen. But the logo actually, let's see.
Oh, the Evie, yeah.
Scarlet honeybee.
Is the
Igrins, what is that?
that's the high resolution near infrared instrument that raises it. Let's see.
That lead scientist.
No, it's not here. I don't have it.
Billboards too, Justice.
Injustice too?
So anyways, the logo for it has an EU on it.
Nice.
So that's nice. So yeah, coming up in the future, so there's the GPI 2. So this is the planet imager that will be here probably sometime early next year. Is the plan. So Notre Dame is the partner institution, main partner institution there. And then GearMoss, so we're getting a next generation adaptive optics system, DNAO, which is 4 lasers. This should arrive in 2028. And so this will be what's called MOAO, so like multi-conjugate adaptive optics. And so this will be adaptive optics at 4 different spots in the sky. And so the main instrument that's associated with that is an instrument that the Canadians are building called GearMoss. And this is a 4 IFU, AO-fed IFUs in the infrared. So it will be able to get resolution better than James Webb at those. We still have to deal with the atmosphere. So okay, not claiming that better than James Webb, but resolution comparable or better than James Webb. And we can do it from the ground, and we can reconfigure all the time. So, so it's survey science. It's going to be a lot of extragalactic stuff. It's going to be at like redshift 2.5, where you can get all the like strong restream optical lines. That's where like our main science case is. And actually, the GearMoss science team is having a meeting in Toronto next week to define the GTO for so the guaranteed time observations for this spectrograph. So
You get a lot of web follow-up stuff here.
yeah, we do simultaneous observations with Webb, and we do SphereX. We've done simultaneous. Even like there's a X-ray telescope on the ISS,
Oh.
which we do a lot of like simultaneous observations of. Yeah, but also the X-ray binary people, like so the like the stellar system people.
How many interesting telescopes are there? There's Chandra for sure, and then that, and then.
Those XMM.
XMM, yeah.
Not
Okay.
that many.
There's not that.
So we're down to 2. 'cause-
We're down to
Chandra's
1.5,
getting ready to go.
basically.
Yeah, yeah.
New Star. New Star.
Just start, yeah, and
Axis, maybe.
forgetting one, the All Sky one. They just
Rosat?
no, not Rosat. That was the older one. Rosita, yeah. Thank you.
Rosita.
Yeah.
Huh. I saw the first all sky map put together.
Okay.
So
Nice.
apparently that was allowed.
Okay.
They cannot share the data put together.
Okay.
Hey, Brian,
Yeah.
2 things. One, I forwarded you the Igrins 2 logo and
Oh, thanks.
it's in your email. And also we're observing with Maroon X currently.
Oh, okay.
So it's
let's end on that.
It's
rather than
the second to
Russian
the
politics.
right on the top screen.
Ooh.
Very nice.
There, you found it.
It's adorable.
Yeah, Jen's deeply involved in migrants too. I am not, so she has the.
Came up with
Yeah, and I helped make
I like
this
that.
logo, and right after it was confirmed, I realized it would have been way better to make the EEV that's on top of the two, the actual two, but it was too late at that
No,
point.
I
No
like
one
it.
wanted
No,
to
I think
do
it's
it.
cool.
Pretty good.
It's going after the galaxy. Oh,
Yeah, I like it.
Awesome. Can we get like a sticker with that or something?
Yeah, do we have stickers of this?
I don't even know where they came from.
The SVG file or the JPEG file, if it happened.
Wow.
Yeah, right. Yeah, exactly.
Yeah, if it happened to.
Where,
if I'm looking at my email.
Yeah.
Oh, I'm sorry, you're a normal person.
Yeah,
Yeah,
We wouldn't
exactly.
do anything.
Well, wait a minute, we might be getting that too
Let's not-
far.
no,
Yeah,
no,
we
no,
need
no.
to.
Okay. So I'll show you guys the Geniers logo since we just finished that up not too long ago. Ooh.
That is-
Oh, you know what? Actually, this is even the.
That is busy.
This is even the last version of the logo. I helped make this, so yeah, it's terrible. Geniers is a Swiss Army knife instrument, so it does basically anything. So this is cross disperse, this is long slit. This actually in the final version of the logo is a picture of Saturn and Titan. It's in here. This is our IFUs. This is a dual AGN system, so two black holes coalescing in the emission.
Swear it looks like Christmas candy.
Titan shadow should be visible on Saturn.
Okay, let's go to Maroon X. Let's do the important stuff. We can call it a night.
Yes,
Yeah.
We're gonna have a plan.
yeah, it's like I think it's they're doing something where the shadow is visible on Saturn's surface. The planets are too small. Not too interested.
Okay, so here we are, Maroon X.
Switching instruments.
Yep, we switch instruments. So if so we actually Jen told the science fold, our tertiary, to go away. So the science fold is now parked, and we're sending the light straight down through the ISS, the instrument support structure, and into the Maroon X fiber. So that's the fiber that goes all the way down to the bottom, the basement.
100-meter long fiber.
Yeah.
So is your setup determined way in advance, or do you do it? In other words, phase one, phase two, and the readiness of the program, or do you wait the night before and do it?
No, we have a phase 2 deadline, and so like we want to make sure by the semester boundary that basically all the programs are ready, so that we have everything in the queue ready, and then that actually sets our like because we have to swap instruments over time. Like we can do 3 instruments at once. Actually, technically we have 4. We have a speckle imager called Alopeke. That's speaking of Hawaiian names, so it's Hawaiian for fox. And this is a speckle imager, so that's basically images on the timescale of the coherence length of the atmosphere, and so it basically beats the atmosphere, and it gets down to diffraction limited seeing for brighter targets like R of 16 and brighter. So it's like on nanosecond timescale, so it takes like 1 billion pictures per second. And then it just like does Fourier transform magic, and then all of a sudden out pops a binary star system or something like that. So that's in our Gemini calibration environment. It's literally just like a little pick-off mirror. Like this like peeks over the corner of the calibration environment. It like steals the light. And so yeah, but we have 4 instruments on at a time. We have now five instruments. And so we set our instrument exchange schedule based off of the like programs that are in the queue. And so we want to make sure that like we have that set up way ahead of time, because I mean, you'll see at CFHT, they do instrument swaps all the time. It's like they're dedicated. Once the thing's on the telescope, that's it. They're on that for the night, if not multiple nights. And so
Super.
yeah.
So when you say you're going to a new source, that whole package is just fired up.
Yeah, so that we have an observing tool, and I don't personally, but Jen does. Yeah, so she'll see the program is in the queue. She will use our software to like basically queue it up in our observation list, and then we'll slew there. Jen will get acquired. So Maroon X actually has its own interface. Normally I have all these screens set up ahead of time. Okay, So here we go. Okay, so this is the MaroonX interface. So I'm VNCing non-interactively into Jen's computer right now. She's VNCing into our MaroonX computer right now. And that MaroonX computer is shared between us and the University of Chicago. So actually every night and every morning, somebody from the University of Chicago team VNCs in and takes calibration data for us. So you can imagine like 1 meter per second precision, you need a lot of like really good calibration data. So actually most of the light that's seen on the bottom here, you see this countdown timer that's down here. So we're exposing right now. This is the science source right here. The circle is the fiber. It's about 1 arc second size. So this is actually, it has its own tip tilt system in the inside of MaroonX. So it compensates for flexure itself. So as we, an atmospheric dispersion. So as we move the telescope, you can see the source moving around a little bit. It'll actually send corrections to the telescope to move the telescope beyond what our guiding system says, because we also have a guide star that we're tracking. And so this exposure was 30 minutes. And so it'll track for 30 minutes. All the other lights here are, you can actually see a series of triangles. 1, 2, 3. And then, 1, 2 down here and 3. These are reflections of our backlit lasers. So the backlit lasers basically triangulate where the source is. It tells the MaroonX software where the source is. So it's got to be in the center of this triangle. And so we have an atmospheric dispersion corrector, which is up in the top right. And then we have like the counts, so a photon counter that's basically measuring, it's picking off some of the light and it's measuring the flux over time. So we can see if things stop guiding, even if we're not looking at this display here, we can see when the counts drop. If clouds come in, we can see that. So the counts will drop because of that. And so all of this down here, so it has a blue channel and a red channel. I'll let you, to your imagination, which is which. And all these little like teeth marks, this is what's called an etalon. And it basically tells us to really high precision which wavelength is where. So it's basically like an arc that's happening all the time. And
It's on the other, like the edges of where the.
exactly. So yeah, the science trace will actually go like here.
Wow.
And so there's like tons of orders. So if you guys were to stick around for another, I would suggest it because you guys have a big day tomorrow. But when the science exposure comes out, it's all these, it's like in a shell spectrograph. So it's all these different orders. And we have etalons on top of every single order. So we have two calibrators in here. One's called a laser frequency comb. Actually, we have 3 calibrators. So laser frequency comb, which gives us the absolute calibration. We have the etalon, which gives us the relative calibration of the wavelengths. And then we have a solar calibrator, which calibrates for basically the spectrum of the sun and radial velocity of the sun. So all of these things are important to remove. This is not my science. This is not my area of
To
expertise.
the end, you get what accuracy?
1 meter per second. Yeah.
Okay. It's
Yeah,
worth
that
it.
is very insane.
Yeah, it is very
That's
insane.
insane.
So I'm happy if I get like 100 kilometers per second. So, this is way.
It's like what, like if you're doing RBS, that's still like the Jupiter-sized planet, right?
No, they can do Earth planets.
Earth size?
Yeah.
Oh.
Yeah, they do like habitable zone, like
Habitable zone Earth size?
Game has changed.
yeah. So yeah, it's come a long ways from like observatory, I guess. So yeah, so that's basically how the night goes. And then yeah, we can be interrupted at any time. Again, anybody in the world can press a button and say, I have a interesting target. If they have a program latent in our queue. We have a lot of targeted opportunity programs. And so we have best laid plans, but then
David
Things happen.
Jones hits a button. and-
David Jones, yeah. Actually, UH is a huge contributor to like the RTO and TOO. Shappy and Karen, yeah,
Karen too.
yeah. I mean, 3I was the interstellar visitor. It was that was a TOO, RTO actually, rapid TOO, And RTOs were basically obligated to salute to them either like now, they can specify like stop everything you're doing and go. Usually it's like within an hour and best effort 24 hours. We usually try to get on them like almost immediately. So I'll just say, if you guys are interested, next Monday, we are also doing a Shadow of the Scientists. We're doing it here, but it's 2 Gemini South, and we're doing a special like pseudo classical observation of 3i Atlas. You guys know what that is?
The one Avi Loeb thinks is a spaceship.
He said he was actually agnostic about that.
Well,
It's the axis ratio.
Medium.com article.
So Karen Meach actually is going to be the science host for that. I'm helping with that. Yeah. So that's so we have a website from UC Santa Cruz, shadow.ucsc.edu. If you guys are interested, it's I think 12:30. Is that right, Jamaica? In the afternoon, just next Monday.
That's right, 12:30 to 2:30.
2:30. So if you want to see observations from another Gemini of the interstellar visitor, and it's moving fast, it's like these are some of the last observations before it goes behind the sun. So yeah, welcome to Hilo.
Rain.
Yeah, it's raining in
It's
Hilo.
clear as heck up top.
Yeah.
So we actually we took data on 3i Atlas and last month, and it made APOD. So Karen Meach was the APOD published it July 17th. Was on there.
that's astronomy picture today.
And who made that image, Jen? Do you happen to know that?
Me and Madi Damani.
Was that a Pan-STARRS or Atlas discovered object?
Atlas.
Atlas.
Yeah. So hold on one second. This is the last thing I'll show you guys.
And then Avi writes another book.
No, the worst part, I think, was he wrote a Medium article, and in it he goes, "This paper did not do a chi-squared. See, look at their figure." Then provides the figure, and then down at the bottom.
This is the image. Jen, did you actually take these data?
Why would you?
Were you on the telescope at the time?
I think it was Matthias might have been. Did
What?
you take the data for 3i Atlas?
I think so. Yeah.
Yeah, I think Matthias and Sunny took some of it. I think there were like multiple days, I think. But
It was a couple days. No. That was for a whole night, I think.
yeah, there were 2 different
The
PIs
object.
from UH.
Yes, I believe so.
But
Right.
one did
there
a
was
spectroscopy.
yeah, no, there was the
and
DD
the
program,
other did imaging.
right?
Yeah.
Yeah, the DD
Yes.
program that came later. That came July 5th, I think, July 4th or July 5th.
Right.
And we also were
Yeah.
taking at that same night, we were taking spectra on Karen's program in the south. And then this
cool.
imaging came just before that, I think a day before that or something like that. And yeah, I think I was actually on Q coordinator at the time, and I was also supporting Karen's program, so it was insane to get these observations. But yeah, so all the different colors are different filters here. And then I guess this is what's that on the right? Is that a color composite from all the different observations?
Yeah, that's the composite image.
Yeah, cool.
Nice.
And it's moving like 4 times as fast as it was when y'all took those observations. So I think it's
Zipping.
Wait, is that all due to the sun or?
proximity.
Yeah, and we were the first ones to see the coma. So no one else saw the coma before we did.
Yeah, I think CFHT also saw it the same night, right?
Yeah.
I think it was like simultaneous observations. There was a lot of people on it.
But it was y'all who Avi was saying did the
Yeah, but how
I'm
many
sorry.
interstellar things do we have now? Is it?
3.
Is it 3?
Yep, this is 3rd, yeah. But I mean, Ruben's coming.
Yeah.
It's here. And so, I mean, it's gonna be, it's gonna be 4i, 5i, 6i, 7i, 8i. I mean,
We're suddenly gonna see way more of these than we were.
I think that Ruben saw this before Pan-STARRS, but Pan-STARRS is the one that discovered it. But going back in the data, I think they did see it.
It was Atlas that discovered.
I'm pretty sure it's Atlas.
it was Atlas,
mean,
but yeah, they data mined afterwards. And
thought
they did
that's-
find, but it was Atlas. Yeah. but they data mined afterwards and they found evidence of it in quite a few different observations. But yeah, anyways, thank you guys so much for coming.
Thank you for having us, Brian.
Yeah.
Enjoy wheat bowling tomorrow. And enjoy Keck and CFHD on Thursday.
I will. I'm gonna enjoy the air conditioning both days.
Air conditioning. Oh, okay.
The elevation.
And you're up all
That's great.
night. We can go to sleep. Is that the night?
I'm going home and I'm refereeing all night, so yeah. Yeah. I'll be doing other things. But yeah, thank you guys so much for coming. It was fun.